It's really great to see you all here, and it's really a great pleasure for me to introduce our first keynote speaker. Some of you know me, I'm really attracted to quotations, and I thought there was one by Sir Winston Churchill that really fits our first speaker and his topic of his talk this morning. True genius resides in the capacity for the evaluation of uncertain, hazardous, and conflicting information. Seems like it could have been written by our speaker, Eric Horvitz, this morning. Eric is, in fact, one of the world's most important researchers on problems and ideas and principles related to sensing and decision-making under uncertainty. He is, of course, for his distinguished research contributions and career, a member of the National Academy of Engineering, a AAAI fellow, a fellow also of the American Association for the Advancement of Science, and the other AAAI, the American Academy of Arts and Sciences. Besides really amazing and important, long-lasting research contributions, Eric is also an amazing mentor to many young scientists around the world, some of whom are now not so young, and a servant to the community. He was the immediate past president of the AAAI. He is on the advisory committee for the NSF Computer Science Directorate and a member of the CCC Council. And last but certainly not least, the deputy managing director for the Microsoft Research Lab here in Redmond. And for that, I'm really grateful because, of course, we work extremely closely together. And so please join me in welcoming our first keynote speaker, Eric Horvitz. Eric?
Well, thanks for that very nice introduction, Peter. So it's certainly, we're in incredibly exciting times. I have to pinch myself once in a while when I put myself back in my grad school days at Stanford in the mid-'80s to late '80s to think about the computation and memory we now have, the connectivity and data, and most of all, the learning and reasoning algorithms we now have to work with data, make decisions under uncertainty, and so on. And I thought today I'd talk a little bit about some opportunities and directions in this realm. Back to my late '80s at Stanford, we were really excited about this idea of capturing uncertain expertise with graphical models, Bayesian networks, where these random variables represented as circles here are connected to other random variables with these arcs that represent dependencies. And this took us, a team, Engelbein and others, about 2 weeks to build by hand, where the numbers came out of the mind of an expert anesthesiologist. And once we built this network, this graph, which represents distinctions you worry about in ICU, intensive care medicine, you can run them by putting any observation in here, blood pressure and CVP, things you could see, running Bayesian network algorithms and picking off probabilities of things you couldn't see, like pulmonary embolus. So these are very exciting graphs, but they were very time-consuming and hard to build. Now, in the 90s and into today, there's really been an explosion of learning methodologies to learn these kinds of graphs from data and learn other kinds of models as well. Here are 3 variables, and you can connect them up in a variety of different ways. And one approach called Bayesian structure search basically looks at all the different combinations using heuristics to form these structures and has a score to score the power of that model to explain data and finds the best model. And that model typically is the one you use to actually go out and actually make predictions in the world of these states you care a lot about that you can't usually see directly. And of course, there are other procedures as well. Beyond making predictions, captured here by this little histogram here from data, we also worry about actions in the world, in the open world. What happens when you take preferences and these uncertainties that are inferred from these models and take action? And so the set of innovations has been marvelous in the space of going from predictions to actions as well. In fact, I like to think about a data to prediction to decision pipeline often. A couple of exciting directions. First of all, this idea that all of a sudden, based on connectivity and communication systems, we have these ambient, you might say, in-stream data resources that just are available. This hit home for me a few years ago when we got access to a cell phone data set that just basically had densities of cell phones at different towers in Rwanda. And Ashish Kapoor and I are working with Nathan Eagle looking at what we can say about what happens to these cell towers and communications more generally when there's an earthquake, about a 6.0 earthquake outside of Rwanda, not far away, the Lake Kivu earthquake. And about 10.5 million phone calls, watching the anomalous calls on these cell towers, only 140 of them from this earthquake, led us, with some interesting probabilistic methods, pinpoint within a few kilometers of the epicenter, just by watching the surge in phone calls at different cell towers as people responded naturally. And we could take a decision model on top of that and compute regions of the country we'd want to do surveillance on, reconnaissance, because of standing disruptions based on the uncertainties there, just from ambient data. But among exciting technical directions in learning right now are causality, really getting to the foundations of core science. Does A really cause B? Or do A and B co-occur with a cause upstream called C? Active learning, thinking a lot about how we can grow a database given the costs and benefits of collecting data. Lifelong learning, building systems that really understand that they're being used over a period of years to decades, and serving a population of people, for example. And then recently, this is some technical work in deep learning. This is like you might call this the third wave of neural nets, where the idea of a neural network that's biologically inspired has been a long-term dream, and it's been foundations of intuitions. But recently, we're seeing notions of taking these multi-layer or cascades of networks where we build inferences at one layer that become inputs to the next layer and so on. And we're actually seeing significant gains, which are actually surprising and give us the sense that maybe there's something to be said about looking very carefully at this third wave of neural nets. Lots of interesting directions going on there. So today I thought I would focus on 4 efforts at Microsoft Research, several of which are developed closely with our partners at several universities and other government agencies and centers in transportation, healthcare, citizen science, and then some hard problems we're facing in trying to build and address the dream of integrative AI, or long-term dream of building intelligent systems. And I think for each one, I'll capture some themes that I think are interesting to this group. And I chose some societally relevant topics. I think people will resonate with them. They also resonate with some of the work that the Microsoft Research Connections team has been funding over the years externally. So first, in transportation, I wanted to stress this work, which is going on for about 7 or 8 years now at Microsoft Research, highlights the notion of the power of heterogeneous data sources and user models. So about 5 or 6 years ago, we were very interested in the Seattle traffic problem. Everyone from Seattle knows that we have the worst traffic in the world. I thought the Bay Area was bad until I got up here. So we started looking at sensors in highway systems. We can get multiple views on traffic from the highway systems. We can get incident reports from the Washington Department of Transportation. Like Nick here is reporting on what's going on in terms of lane coverage and so on. We could go out to the web for all these reports, weather reports, major event schedules. We could grab a large map of road topology and properties. Every single road is captured. And of course, day and time. And build a large database that we could then use to make predictions. And we could use that Bayesian structure search to build out one of these graphs that will tell us, for different parts of the highway, the likelihood of a clog, for example, and then field it on portable smartphones, of course, people's pockets. And provide this kind of an inference here where you see this little wedge here showing the max likely time that a jam will last until it melts, as well as the system's confidence. So the system's reasoning about its own confidence and sharing that with people. And it was a lot of fun and exciting to build this system, but we also started learning about the value of these systems in people's pockets. Well, what did people use them for exactly? It turns out that most people in Seattle fashion themselves as Seattle traffic experts. They don't need to have inference to tell them it's a rush hour on a rainy night going to Kirkland from Redmond is going to be packed and terrible on the 405 North. So we actually started thinking about a user perspective on machine learning, which is a machine has a world model, and it's making inferences, for example, about traffic. A human being, this Seattle traffic expert with lots of experience, is looking out, and she or he have their own inferences. And could we build systems that could have a model of what people thought, and then consider an estimation or approximation of what people think and what it thinks is per gold standard, and work with people to share most important information possible. This led to our work on models of surprise. Can we learn with machine learning algorithms what will surprise people now and in the future? And the idea here is we have a human forecaster who understands major events, weather, time and day, and holiday or not. We could take slugs of 15-minute segments of time over a period of years and build an expectation model, and then find these exotic flows and clogs in the highway, which are like 1 in 1,000 or 1 in 100. We can set the threshold. And then we want to store a database of human surprises about Seattle traffic in this case. Our system has a bigger purview about what's going on in the world, including accidents happening, the dynamics over time, sporting events that the expert might not know about, the topology of the road, and so on. And we can actually correlate the human surprises with not just what the system knows now, but what it might know 10 minutes ago or an hour ago. So we're going to go back in time now. And here's the